Next, we discuss the third law of thermodynamics. The previous section described the various contributions of matter and energy dispersal that contribute to the entropy of a system. With these contributions in mind, consider the entropy of a pure, perfectly crystalline solid possessing no kinetic energy whatsoever. That is, at a temperature of absolute zero. This system may be described by a single microstate, as its purity, perfect crystallinity, and complete lack of motion means that there is only one possible location for each identical atom or molecule comprising the crystal. And if you remember what W is, that's a microstate. And in this particular, or under these set of conditions, we have one available arrangement of all these particles. According to the Boltzmann equation, the entropy of the system is zero. And here you can see that. The entropy of the system is equal to the Boltzmann constant times the natural log of however many microstates you have, in this case is 1, and that would equal 0. This limiting condition for a system's entropy represents the third law of thermodynamics. The entropy of a pure, perfect crystalline substance at 0K is 0. And you can't ever have negative entropy, but this gives us a nice little benchmark baseline for entropy for a system. We can make careful calorimetric. In section 16.3, we introduce the second and third law of thermodynamics. And so the second law of thermodynamics, we're going to start with this right here. In the quest to identify a property that may reliably predict the spontaneity of a process, we've already identified a promising candidate, and that is to look at the entropy. Processes that involve an increase in entropy of a system, that is, delta S of the system is greater than 0, are often very spontaneous. However, examples to the contrary are plentiful, and we will see examples of this later. By expanding consideration of entropy changes to include the surroundings, we may reach a significant conclusion regarding the relation between this property and spontaneity. So in thermodynamic models, the system and surroundings comprise everything, that is, the universe. And so the following is true. We can sort of think about the entropy change of the universe as being the summation of two components, and that is the entropy change of a system plus the entropy change of everything else, which we call the surroundings. To illustrate this relation, consider again the process of heat flow between two objects, one identified as the system and the other identified as the surroundings. There are three possibilities for such a process. The first possibility is this. The objects are at different temperatures, and heat flows from the hotter object to the cooler object. This is always observed to occur spontaneously. Designating the hotter object as the system and invoking the definition of entropy yields the following. And here we go. Here we see our entropy change equation again, and it's written out in two ways. Here we've got the entropy change of the system on the left and the entropy change of the surroundings on the right. And you'll notice that there is a sign difference in Q rev here in the numerator between both equations. The arithmetic signs of Q rev denote the loss of heat by the system and the gain of heat by the surroundings. That is, heat is flowing from the system to the surroundings in this example. Since the temperature of the system is greater than the temperature of the surroundings in this scenario, the magnitude of the entropy change for the surroundings will be greater than that for the system. And so the sum of delta S system and delta S surroundings will yield a positive value for delta S of the universe. This process involves an increase in the entropy of the universe. The second possibility involves this. The objects are at different temperatures and heat flows from the cooler to the hotter object. This is never observed to occur spontaneously. Again, designating the hotter object as the system and invoking the definition for entropy yields the following. Here we have our two equations again, but you will see that the signs have now changed for Q rev. The arithmetic signs of Q rev denote the gain of heat by the system and the loss of heat by the surroundings. The magnitude of the entropy change for the surroundings will again be greater than that for the system, but in this case the signs of the heat changes will yield a negative value for delta S of the universe. This process involves a decrease in the entropy of the universe, and note that this process does not occur spontaneously. The third possibility is this. The temperature difference between the two objects is infinitesimally small. That is, the temperature of the system is about equal to the temperature of the surroundings, and so the heat flow is thermodynamically reversible. See the previous section's discussion on reversible processes. In this case, the system and surroundings experience entropy changes that are equal in magnitude and therefore sum to yield a value of 0 for delta S of the universe. This process involves no change in entropy of the universe. So considering these three possibilities, we see here that these results lead to a profound statement regarding the relation between entropy and spontaneity, known as the second law of thermodynamics, and that is this: all spontaneous changes cause an increase in the entropy of the universe. If you have a process that increases the entropy of the universe, then that particular process is indeed spontaneous. And here's a summary in table 16.1 of what we've just discussed. If the entropy change of the universe is greater than 0 for a process, then that process is spontaneous. If the entropy change of the universe is less than 0 or negative, then that process that is causing that to happen is non-spontaneous. However, if the entropy change of the universe is about equal to 0, then we're talking about a reversible process, meaning that that process or system is at equilibrium. Your book rightfully points out that for many realistic applications, the surroundings are vast in comparison to the system. In such cases, the heat gained or lost by the surroundings as a result of some process represents a very small, nearly infinitesimal fraction of its total thermal energy. For example, a combustion of a fuel and air involves transfer of heat from a system to surroundings that are infinitely more massive, such as the Earth's atmosphere. As a result, Q surrounding is a good approximation of Q rev, meaning when you undergo this combustion process for, gasoline in your car, are you really going to change the heat of the surroundings that much? Because the surroundings represents the Earth's atmosphere. So we can use this approximation of Q surroundings as being a reversible process, and the second law may be stated as the following. And here all we've done is taken the same equation that we've seen before up above, and we've replaced this delta S of surroundings with this particular expression right here, the heat of the surroundings divided by T. Let's look at example 16.4 together to try to expound upon this idea. The question is, will ice spontaneously melt? The entropy change for the process, and here it is, solid ice going to liquid, water, is 22.1 joules per Kelvin. Again, that is a measure of entropy change for this process, and requires that the surroundings transfer 6 kilojoules of heat to the system, that is, the ice. Is the process spontaneous at negative 10 degrees C? And is it spontaneous at positive 10 degrees C? While we might already know the answer to this qualitatively, we should be able to describe this mathematically as well. So here's the solution as given by your book. We can assess the spontaneity of the process numerically by calculating the entropy change of the universe. If the change of entropy of the universe is positive, then the process is spontaneous. At both temperatures, delta S of the system is 22.1 joules per Kelvin, and the heat of the surroundings is negative 6 kilojoules. At negative 10 degrees C, or in Kelvin, that's 263.15, the following is true. Here we see our equation up above once again, where we try to determine the entropy change of the universe. We go ahead and plug in our entropy of the system right here, 22.1. And then for delta S of the surroundings, we're going to consider the Q, or heat of surroundings, divided by the temperature. And that's what we plug in here. And notice that the heat is given in joules to keep our units consistent. When we calculate this result, we get a negative number, telling us that ice would not spontaneously melt at negative 10 degrees C, as it would make the entropy change of the universe negative. Therefore, this would not be a spontaneous process. However, at a positive 10 degrees C, I think most of us know that ice would spontaneously melt, and if we were to calculate the change of entropy of the universe once again, we would see that we get a positive value. Because the entropy change of the universe is positive under these conditions, we know that melting ice at 10 degrees C is spontaneous. Next, we discuss the third law of thermodynamics, and you should definitely read through this section to gain a better understanding of what's going on here. But essentially it's this. We've been talking about entropy changes in this past section. However, the question is, what is the absolute entropy of a system, and can there be one? Well, it turns out that there can. Consider this. Imagine if you have a system that can be described by a single microstate, just one. And this particular system is going to be a perfect, pure, crystalline substance that has a complete lack of motion, meaning that it has no kinetic energy whatsoever, and this would occur only at absolute zero of 0K. This means that there would only be one particular microstate for such system. And if you were to go back and plug in 1 for microstates, W, in our Boltzmann equation, we would see that the natural log of 1 is indeed 0. The idea here is this. The entropy, the absolute entropy of a system in this state is 0. And entropy can only get larger from there. This leads us to the third law of thermodynamics that states that the entropy of a pure crystalline perfect substance at 0K is indeed 0. If that's the case, this allows us to give a benchmark entropy value for systems in different states, as we know that we can always reference the system back to the pure perfect crystalline substance at 0K, because we know that the entropy would be 0 in that state. We can make careful calorimetric measurements to determine the temperature dependence of a substance's entropy and to derive absolute entropy values under specific conditions. Standard entropies are often given the label right here, S of 298, that is 298 Kelvin, and then we have a not symbol, meaning standard, for values determined for 1 mole of a substance at a pressure of 1 bar and a temperature of 298 K. So what's important here? You should remember that standard states, such as standard entropy, relies on certain conditions, such as temperature being 298 Kelvin, the system being under a pressure of 1 bar, and the fact that we're talking about 1 mole of a substance. The standard entropy change, delta S naught, for any process may be computed from the following standard entropies of its reactants and product species, like the following. Here we have the standard entropy change is equal to the standard entropies of all the products in a reaction or a process, and we subtract off the standard entropies of all the reactants. Here, the Greek letter nu represents the stoichiometric coefficients in the balanced chemical equation representing the process. Here on the following page in table 16.2, we see actually a rather small list of standard entropies for a variety of substances. Please note that standard entropies are in units of joules per mole Kelvin, because to have a standard entropy, you must be talking about 1 mole of a substance, as per the definition that we've described prior. Let's go ahead and do example 16.5 together, where we would determine the standard entropy change for a very simple process, and that is the condensing of water. Here we have water vapor condensing to water liquid, and we can determine the standard entropy change for this process. To do this, we must set up our standard entropy change equation shown down below. Here, the entropy change of this process is going to be the standard entropy of the product, that is water liquid, and we're going to subtract off the standard entropy of the reactant, and that is here, water vapor. You can find these values up above in the table. Let's take a look. Liquid water has a standard entropy of 69.91. The authors of our textbook has decided to round this number off to 70, which is fine. So here I plug in 70 joules per mole Kelvin for my product entropy, and I'm going to subtract off the value, the entropy value for gaseous water, which again I can find in this table up above, which is up here listed as 188.71. The authors of your textbook has decided to put in 188.8, which is okay for this example. When you subtract these two numbers, you get a negative value for your entropy change. We should all recognize the fact that the entropy change for gaseous water going to liquid water should indeed be negative, because you're going from a more disordered system to a more ordered system as you go from the gas phase to the liquid phase. You should definitely read through example 16.6. In this example, this involves 2 reactants and 2 products. You will have to add the entropies of the products together and then subtract off the entropies of the reactants after you've added them together. And this example shows you this below. This is a very standard type of problem that you could expect to see on an exam. Please note that you never have to sit down and memorize standard entropy values at all, as these would be provided. One thing to note is that some of your homework problems may not provide standard entropies for you in the problem. But that's okay. You're going to be expected to look these values up to solve those problems. And your book provides many standard entropies for you and offers a good reference for this type of thing. If you go to Appendix G in your book, and I'm going to click on this right here to take me to Appendix G, you will see a giant table that provides standard thermodynamic properties for selected substances. And if you look here on the left, you've got a particular substance listed and the state of matter that it's in. And you're given 3 values. If you look over here on the right, you will find the standard entropies for all of these substances listed. And you will probably use some of these in your homework.